Welcome all, I'm Pidad D'Souza, File System Performance Architect. With me I have John Lewars, Senior Technical Staff Member, Performance Development Lead at IBM. It's our pleasure to present at SDC on the topic of optimizing system performance. In the recent years, a large amount of data is generated and processed by machines, applications, and connected devices. Advancement in data processing is required in the fields of HPC, AI, and ML to improve business insights, enhancing customer engagements, and other aspects of research. Data scientists are continually looking for effective ways to access and manipulate such data with lower latencies and higher throughput. File systems play a vital role and influences overall application performance. Today, we are going to take you through various components of system that influence file system performance, how benchmarks can be used to analyze the bottlenecks among these components. We also detail these analyses through some examples. On the right side, you see a system architecture wherein storage devices such as disks and NVMEs, using which a file system is created by the IO server. And this file system is exported to the clients which are running either CPU-based applications or GPU-based applications. And these clients access the file system through different Ethernet or InfiniBand network cards. In such a complex system wherein multiple components like processors, accelerators, memory subsystem, operating system, file system, and network and storage subsystems are involved, one need to evaluate each of those components' performance using micro benchmarks pertaining to those components. For example, general matrix benchmark is used to measure the performance of the CPU. Similarly, other benchmarks such as stream, MPI benchmarks. For IO, we have IOR, MDTest, and FIO benchmarks. Additionally, one need to use the profiling and monitoring tools in order to measure the counters values pertaining to processors, GPUs, or network devices. And also these tools help us to trace the application to identify the hot routines in the application. And IO profilers for MP applications such as Darshan help us to trace the IO calls within the application to understand the pattern of IO accesses. And similarly, some of the diagnostic tools such as IBM Diagnet can be used to identify the errors in the network layers. Here is an example of running a stream benchmark to measure the achievable memory bandwidth, wherein you can see that various functions such as copy, scale, add, and triad are run on the system to measure the bandwidth of those memories. And tools such as dstat shows that CPU utilization and how many processor threads are blocked or running, and memory utilization on the system, and also data transfer on the network devices. In HPC applications, parallel tasks are being run, which basically does similar operations in a synchronized manner. In such a lockstep mannered applications, parallelism is often limited by the slowest component. Workloads such as AI, ML also share the similar characteristics of HPC applications, wherein they too work in a lockstep manner. And while such applications using a clustered file system, the performance is often as fast as the slowest component. Having said that, in order to analyze the bottlenecks, one can use micro benchmarks in two ways. First, it provides a means to independently validate each of those system components and investigate any possible bottlenecks in those components across the cluster. You can also use these bottlenecks to detect transient failures, which may require multiple runs to identify exact location of bottlenecks. Secondly, you can use these same micro benchmarks to simulate certain aspects of your application wherein specific patterns such as a sequential or random read patterns, large data transfers or small data transfers, you can look at specific area in the code and identify the bottleneck using this benchmark. In this benchmark-based simulation, you can configure or do a code refactor to improve your performance. Some examples may include in adaptive routing enablement or increasing number of network ports or adapters. Now let's look at how we can characterize the I/O using some of these application profiling. At the top side, you can see that here same dstat is used to track the amount of data either written or read on the system. It also gives the size of data transfers. And additionally, at the bottom, you can use some of the file system specific utilities. In this example, we are using IBM Spectrum Scale IOHIST utility, which helps us to identify the data transfer sizes and along with the timestamp. Similarly, one can use low-weight, lightweight file system tracers to trace each individual inodes and their offsets in the file and data sizes to identify the pattern of access, sequential random accesses. And using such data, one can plot those data against timeline. And in this example, you can see on the left side, the blue line indicates disk IO read bandwidth, and the red line indicates applications read bandwidth. You can clearly see that application bandwidth is manifold higher than the disk bandwidth. Why is it happening so? The main reason is file system is caching the data read by the disk, and the application is reissuing some of the IOs, which is leading to a higher bandwidth at the application side. So this clearly indicates that tuning of cache size will help improve the streaming throughput, but be aware that increasing such a cache size may impact the memory footprint on the system and have a negative impact on the other applications running on the system. Now let's look at some of the components and the bottlenecks coming from some of these components. To start with, let's look at the NUMA-based systems. In NUMA-based systems, a given processor has a local memory. In this case, proc0 has a local memory 0. Access of memory from that has a lower latency. And if it is trying to access a memory from another processor, which is a remote access, the latency going to be higher. One need to analyze such a cross-socket memory accesses using tools like NumaStat. And as a mitigation strategy, you can use NumaWare file system, wherein such file system can use NUMA-specific adapters to do a data transfer to minimize the cross-socket memory accesses. Similarly, one can build in NUMA awareness in the application by affinitizing the threads and reducing the latency, which eventually translate into a higher throughput. In AI ML applications, which are generally GPU-centric, because of the nature of massive parallelism they require, GPUs are the best suited for such applications. However, in order for GPU to compute, it needs to have the data within its memory buffer. It will read from the storage as shown in the top right corner of the diagram. There are 4 steps involved wherein storage data is read into the file system pool, and at the client side it is transferred to application and then to the GPU. Using NVIDIA's GPU Direct Storage technology, one can minimize these steps into 2 as shown in the right bottom. Here, data from the storage is copied into a GPU using RDMA. How does it help altogether in applications? Here on the left bottom, in our lab setup, we have used IBM Elastic Storage Systems, ESS 3200, 2 building blocks, and we have used 2 DGX A100 systems from NVIDIA. In scenario 1, we used 1 DGX A100 system, and scenario 2, we used 2 DGX A100 system. In scenario 1, as highlighted in the box here, we could reach up to 49 GB per second of a bandwidth using GDS as against 22 Gbps without GDS. Similarly, you can see the similar benefit in the scenario 2. These measurements are done using NVIDIA's GDS IO utility. Approximately 2x of throughput improvement is seen. At the same time, we also see that CPU utilization on the client side is drastically reduced. With that, I would call upon John Lewars to take us through some of the examples of bottleneck analysis in the network and storage components.
Hi, I'm John Lewars. I'm the Spectrum Scale Performance Development Lead, and I'm going to follow up on some material that Pidad presented, chart 5, where he pointed out that the role of microbenchmarks really, we have 2 aspects. Number 1, we can use microbenchmarks to validate the health of the system, that all components are performing as expected. We can also use them to drill down into various aspects of application performance. So we're going to walk through an example here. The example assumes that you've done some kind of profiling, counter analysis, maybe MPI traces, GPFS or file system traces, something that's led you to a given aspect of the application where you have a bottleneck. Let's assume that that bottleneck is a streaming I/O workload, sequential streaming workload. And if you're going to use microbenchmarks to emulate what's going on and to try to drill down in that aspect of your code, you want to make sure that you're running the benchmarks in a manner that's representative of how the application's running. For example, if the application's using direct I/O, make sure that you run your microbenchmarks in direct I/O mode. You try to also configure the application and the benchmark in the same manner, such as how you're doing your threading, right? If you're using an OpenMP model, you want to use the same kind of model in the microbenchmark, a similar thread count. You can do analysis, for example. It might be easier at times to change the message size within a microbenchmark rather than refactoring the application, changing the number of MPI tasks as well. You might find out where the optimal performance is seen with the microbenchmark. Let's walk through an example here in which we look at some components that will limit performance of a streaming I/O workload. So we've got 2 scenarios here. We're starting with a single client connected by a 10 gigabit link, and it's directly connected to a storage server which has a single hard drive. And that hard drive is only getting 100 megabytes a second. So in this example, your bottleneck is going to be back on the storage because you have about 10 times more bandwidth at the network layer. Now we can extend this example. What happens if we now add more hard drives? Let's say we have 20 hard drives back on the storage server. You need to think too as well as to if there are additional bottlenecks on the server side, for example, PCI bus limitations that might prevent you from hitting the bandwidth that each drive can hit in aggregate. So you might do some low-level block measurements to try to figure out what the server can really deliver. But let's say you do those measurements, the server's scaling perfectly in terms of the drives. Now your bandwidth or your bottleneck is going to be limited by the network performance in this case. So you want to be individually measuring the network with some kind of network benchmark. In GPFS, you might use NSD-perf, or for another file system, you might use IPerf or a low-level RDMA benchmark. And you could use something like FIO for your block level measurement back on the server side. Of course, once you've created a file system, you won't be able to do write benchmarks to the same block devices that comprise that file system. So you'd want to do that kind of analysis up front before you create the file system. Also consider the scaling of any additional clients and servers that you may add. Potentially, you could be limited by the slowest server or client in the configuration, right? And that depends on the characteristics of the application. If, for example, you're running in lockstep mode, you have frequent synchronization points such that the slowest node really will be the bottleneck. So in addition to what's going on directly on the client and server and the network adapters that are directly connected, you also have to consider what's going on in the network itself. And here's just a simple example. We've reduced the number of ports that you would typically see in more modern switches here, just showing sort of a snippet here. The point of this being that in this switch configuration where we have two switches which are joined together with only two links between the switches, and we're using the other ports which we would normally have connecting the switches, we're using those for node connection. So what we're depicting in this example is a 3-to-1 blocking factor network such that we have 3 times as many clients that are feeding into each switch compared to how many links go out to the outbound switch. So in this case, aggregate bandwidth could be limited by the network itself. That's just another example of a potential bottleneck. So now we'll divide these bottlenecks into 2 classes, really. So inconsistent bottlenecks, let's say issues that will cause inconsistencies within your performance measurements. These examples of these kinds of problems could be some kind of flaky link on one of the clients or servers or switch port. Also any kind of congestion, let's say network fabric issues could often result in inconsistent performance. And the way that we would debug these kind of issues is typically we would use, if we were dealing with an IP network, we might use TCP dump to look at the low-level counters, ETH tools, the switch counters themselves. If we're dealing with RDMA, we would look at RDMA counters, but typically we often go back to tried and true tools such as if we were dealing with Mellanox, let's say UFM, NeoHost, or IB Diagnet to look for, let's say, any kind of errors on the network. If you have those kinds of problems at the network level, particularly in the fabric, congestion issues can often be addressed by enabling adaptive routing, changing your routing algorithms, any kind of, let's say, bottlenecks within the node. One point we've seen on some of the later AMD machines, we really need to do PCI tuning, enabling PCI relaxed ordering. Packet loss is a classic example of an intermittent problem. So once you clean up your network and you use micro benchmarks to validate that the network is clean, you have to be prepared to continue doing that throughout the process because sometimes the network may change, right? Problems will creep in even after you may have cleaned it up. And another potential approach would be refactoring the application. If you're finding that you need to, as we showed in the earlier example, change configuration options like threading or binding. Those are all examples of approaches that you can use within the micro benchmark. And sometimes it can be easier to work with a micro benchmark rather than having to do those changes directly in your application. So another example of that kind of refactoring might be changing the message size, right? Which sometimes could be more difficult to do within the application because that may require sort of refactoring how the data is accessed. Okay, and then now the kinds of problems that we would see more, let's say, consistently on the network might be if we had some kind of PCI width configuration problem, right? The number of lanes configured is a problem that typically remains a constant issue. Obviously, the bandwidth that you're getting from the adapter itself can be a limitation, as well as the switch ports. If cables have timed at the wrong link speed, for example, that tends to be a consistent problem until you reboot. So in this example here, we're showing some bandwidth measurements where we're scaling up the number of tasks per node, and you might try those kinds of measurements yourself with different systems. You have access to different systems, right? If you know that your application is streaming IO limited, you want to pick the right system if you have access to more than one system, right? Make sure that you're picking a more modern system. Here we're showing an older system with FDR links. Obviously, if you know that your application is vulnerable to these kinds of limits, you will want to try to run on ideally HDR, NDR, or at least EDR. All right, so in conclusion, what we tried to do here is show the relationship between the various components that will really dictate the performance of your parallel application of file system workloads, right? Depending upon the type of application you're using, processors, GPUs, the memory subsystem, the operating system tuning parameters, file system configuration, the way your network and storage subsystems are laid out, those can all come into play. And often the slowest limiting component will really be what dictates your performance. You can use micro benchmarks to try to validate the overall health of your system, make sure that components are performing as expected, continue to do that throughout the work that you're doing on the application, because things can change over time. And you can also use these micro benchmarks to try to simulate what's going on in your application, do some investigation with the various approaches we described in terms of looking at traces, profiling, counters, try to figure out where your bottlenecks are, and then you can simulate a similar access pattern using micro benchmarks. So it's all about really making sure that all your components are running as expected, that you've looked for all the appropriate, in all the appropriate places for bottlenecks, and you've tried the kind of mitigation strategies that we've discussed. So we'd like to acknowledge some other IBMers that have helped in terms of the materials we presented here. So our thanks to the people here that were listing on this chart. We have some references here as well that refer back to some of the components, some of the aspects that we've talked about within this presentation. And if you could, it would be great if you could take a moment to rate this session, as your feedback is important to us. I want to thank you for your time today.